This chart shows the expected drop in a galaxy's rotation speed based on its visible mass, plotted against the actual observed velocities. According to Newtonian gravity, stars at the outer edge of a galaxy should orbit slower than those near the dense center. Instead, observation shows the velocity curve flattening out, with outer stars moving far too fast. Standard physics attempts to solve this mathematical gap by proposing invisible particles. By calculating exactly how much extra mass is needed to keep these galaxies from flying apart, researchers have populated the universe with a placeholder called dark matter. At the cosmic scale, astronomers measuring distant supernovae encountered a second discrepancy. The expansion of the universe is accelerating. Because gravity should be slowing that expansion down, physics introduced a second placeholder, dark energy, a mysterious repulsive force driving galaxies apart. These two placeholders currently account for 95% of the standard cosmological model. Almost the entire universe is comprised of theoretical materials that emit no light, block no radiation, and consistently evade direct detection. This persistent failure to detect physical particles suggests we may not be missing mass or energy at all. Patching equations with invisible substances allows the math to function, but it obscures the possibility that our foundational model of spacetime is mathematically flawed. The Relational Action Framework, or RAF, proposes that geometric space and time are not the fundamental bedrock of reality. In this framework, standard spacetime is a rendered map projected from a deeper, invisible web of relational connections. Mass is redefined here. It is the mathematical degree of stable closure within that relational field, rather than an intrinsic property of a physical object. Changing the definition of mass reveals the entire dark sector as a massive accounting error of relational structure. The mathematical foundation of RAF begins with the premise that reality is built from slices of an undivided whole, governed by primitive relations between them. Every primitive relation has two components: connection strength, represented as ρ, and phase, represented as phi. We must differentiate geometric distance, how far things appear in space, from closure distance, which tracks how deeply connected they remain in the underlying network. High closure closeness across large geometric distances explains quantum entanglement natively. The particles aren't signaling across space, they remain adjacent in the underlying network. RAF defines time as the accumulated internal resequencing of a stabilized mathematical state. This explains why a photon experiences no proper time. It is pure propagation without the internally stabilized resequencing that generates the experience of duration. Because geometry and time are derived downstream effects, using them as primary metrics to measure the cosmos guarantees mathematical errors at galactic scales. The standard Poisson equation for gravity assumes that only localized, visible knots of matter generate gravitational mass. RAF corrects this by recognizing that closure energy remains distributed in the background network. This requires a new variable for effective hidden closure density, ρ_hid. The first component of this hidden density term is relational amplitude gradients, storing the persistent support of the system. The second is the phase gradient, storing relational transport tension. The third is frustration density, unresolved closure tension from connections unable to reach perfect phase alignment. To produce flat rotation curves, the total effective density of the galaxy must scale inversely with the square of the radius. A large-scale closure frustration decaying at this inverse square rate yields a hidden mass integral scaling linearly with distance. This derivation outputs a constant velocity variable, matching observed galactic rotation without the need for dark particles. Dark matter is the gravitational effect of non-luminous persistent structure, holding the galaxy together through the background network. At the cosmic scale, the problem of accelerated expansion is resolved by the same relational logic. The global closure tension potential equation measures the large-scale unresolved closure incompatibility across the universe. The entire universe operates as a massively over-constrained relational network that evolves to reduce its internal mathematical tension. The network relaxes this tension by increasing the spatial separation between incompatible closure regions. When global frustration is reduced by increasing volume, the effective closure pressure becomes negative. This negative pressure is then applied to the standard Friedmann acceleration equation used in cosmology. Plugging the RAF negative closure pressure into the equation forces a mathematical transition. The negative pressure forces the output of the acceleration equation to become positive. In the RAF framework, dark energy is simply the thermodynamic relaxation of closure tension, forcing the universe's rendered geometry to expand outward. Standard cosmology relies on invisible mass to balance its density equations. RAF replaces this inventory of particles with a structural calculation. The RAF master accounting equation defines effective density as visible matter plus support structure minus instability. The support structure term accounts for hidden relational connections. When we miss these connections, we underestimate mass and incorrectly label the effect as dark matter. The instability term accounts for unresolved network tension. Failing to track this tension leads us to perceive anomalous expansion, which we incorrectly label as dark energy. Dark matter and dark energy are opposite operational regimes of the same underlying relational mathematics. This model makes several testable predictions. First, particle searches for dark matter will continually yield null results, because there is no dark particle to be found. Second, a galaxy's apparent dark matter profile will correlate directly with its phase stability and structural coherence, rather than its visible mass alone. Third, certain cosmic systems will exhibit less gravitational effect than expected, because their structural closure was overestimated. We can view the universe as a complex, tangled knot of structural threads, slowly loosening to resolve its own internal tension. The universe is a single relational structure, dynamically reconfiguring itself to find stability, rather than a box filled with isolated objects expanding into emptiness.